This is chapter 18. We're going to start talking about DC circuits, which is direct current circuits. We're only going to talk about resistors. Your AP test does not cover capacitors. So today we'll talk about resistors in series. It's very easy, so it'll be a very short day. And hopefully you'll enjoy it at least a little bit. So today we'll talk about the electromotive force, and that's like what's kind of pumping the electrons along. And we'll solve resistors in a series circuit. So first of all, the electromotive force is usually your EMF. You'll see the word or the letters EMF, or this funny little squiggly epsilon. And it's the electric field that's pumping the electrons through the circuit. What?
You said it's backwards story.
Yep.
Is that epsilon?
Yes. So in most circuits, this is the battery. The battery creates a potential difference from positive to negative, and that is an electric field that is generated, and that causes the electrons to move through the wire, creating your electricity. This does not have to be caused by the battery. It can be caused by any changing electric field. So if you ran a wire through a magnet, we call that induction. So if you have like a magnet here, as you get closer to the field, it's going to push the electrons. And remember, whenever you have moving electrons, you have electricity. So you have an electromotive force that you could actually measure, even though you don't have a battery.
So we could have found the electromotive force in what we talked about last chapter.
The electromotive force was caused by the battery, which is voltage. What I'm saying is it doesn't have to be caused by the battery. So any changing electromagnetic field, so any electric field or magnetic field, because magnetic and electric fields work together. So you could move a wire through a magnetic field. So if this is your magnet, as it gets closer, it gets stronger and stronger, and then it starts to get weaker and weaker. So as it moves, it's changing through that electromagnetic field. If you just had like a magnetic field of like 5, it's gonna as you go from 0 to 5, it'll move it, and then it'll stay constant, and then it won't move. And then as you move it out of the field, it'll move again. So as long as that field changes, the electrons move.
Okay.
Think of it as tires spinning. As long as your tires are spinning, you're moving. But as soon as they're not spinning, you're not moving. So it's kind of, think of it as a pump. And usually it's caused by the battery, but it doesn't have to. I've lost mine.
Yeah, but when you set more vectors on, it amplifies the
Okay, so electromotive force. All batteries have some sort of internal resistance. So the EMF of the battery is actually less than the voltage of the battery. So if it says 9 volts, it might only have 8 volts that it's actually using to push those electrons with, because the battery itself has some sort of resistance. If we wanted to calculate that, which you don't really need to know this too much for the AP test, but there's a couple of questions on your homework. You can find the electromotive force by finding the voltage of the battery and adding it to the current and the resistance of the battery. Although a part of me thinks that might be negative. I would double check that in your book.
Yeah,
It's negative?
I think, wait, let's see. Oh, wait, never mind, you're good.
No, it's good? It is positive?
I'm just thinking
Okay.
in the book, it's a change of V equals the funny with E minus IR. So it's reversed.
Oh, okay. So it's still the same
Yep.
equation. Okay. Oh, right. And we got one red cup over there. So resistors are very simple devices, such as light bulbs. Or I can actually bring out a little resistor. And it has like a different type of wire, or maybe like a little spiral of things. But it could be as simple as a light bulb, or even a heating element, like the heaters. Now, resistors are used either as a light bulb to output energy, so a light bulb is used to see things, right, to create light. A heating element, as it says, to create heat, so we're outputting energy. Or we can use the little tiny bits of wire that are different than the wire in our circuit to change the current or change the voltage. And it's not really change the voltage, right, because the voltage is coming in from the battery. At least in simple circuits, we can use it to change voltage if we put it in a parallel circuit. And it kind of, since it changes, the resistance isn't going to change, so since it changes the voltage, it's going to change the current. Or if it changes the current, it's going to change the voltage. And this allows it to not overheat, to not get too much current and explode or melt the wire. And so we use resistors, and you see lots of resistors in your computer parts, most of your electronic hardware. You're going to see all these little resistors and transistors and capacitors. So they're used either to output some sort of energy or to control the circuit. Because this bit might need more power or more current than this bit might be to run. Or if you put too much current into it, it could get too hot and break, which we don't. So resistors in series. Resistors can be arranged in line with each other. So you did this last week, and you had your power supply, you had your ammeter, and you had your resistor, and they're all in one single loop. So if you followed along in one line, that was in series. And then if you looked at your voltmeter, it was kind of outside of that loop, and we took two wires from the voltmeter and we had to put it around the resistor. Well, now you had two loops. That would be parallel. Today we're just going to kind of focus on resistors in series. You'll see that they're very easy. Questions? So here are the rules for resistors in series. You can have as many resistors in a line that you want. There is no limit. This picture here has two.
So what if you have so many resistors that the current just stops going through?
I mean, you'd have to have a very low current and very high resistance, but you'd still be able to calculate something according to our numbers.
Because you couldn't have a current of 0, because then the voltage would be 0.
Right. So as long as you have all three, you'll be able to calculate. It might be really, really small, though. All right. The resistors maintain their own resistance. So the resistance of each resistor is constant. The only thing that's going to change is the current and the voltage. So when you're trying to solve these circuits, you'll add up your resistors, and then you'll find the total current and the total voltage. Now the total current for all the resistors added up should be the same, and the voltage will be added. So if you add the voltage of each individual resistor, they'll add up to equal the total voltage of the battery, or the total of the circuit. And the current, I, in each one of these resistors, let's say it's 2, is going to be 2 for every single one of them. So if you want to find the resistance for the entire circuit, you just add them up, which is pretty easy. And as long as they're in series, that's going to work. In parallel, it's not the same thing. So that's why we're just covering series today. So we can take a bunch of resistors in a series and we can condense them down to a single resistor. This would be the resistance for the circuit. This is how we solve circuits. The first step, and I don't think that's up there, but the first step is to find the equivalent resistance of the circuit. equivalent something. And for series, you just add your resistors. The next step is you usually know your voltage. That's usually given. So now that you know the total voltage, which is the battery, and you know the total resistance, you can solve for the current. So since in series current is constant, the current you just found for the total is going to be the same current for every single resistor that's on there. And then once you know all the resistances for each one of them, now you know the current for each one, you can use V equals IR to solve for V for each one. So now you'll know the current, the voltage, and the resistance of every single resistor and the total as a circuit. And the last little step that your book doesn't make you do all the time is you solve for power. P equals IV. Solve for P. And I'll show you a grid and how to solve all of this. And you can double check. Now for series, it's kind of like, why do I have to put it all in a grid? This is really easy, da-da-da-da-da. But when we get to complex circuits where you have some series and some parallel and they're all nested inside of each other, solving for power is really nice. You can be like, did I make a mistake or not? You get power one way by getting it like 500 and then get power another and getting it like 2,000. You're like, oh no, I made a mistake. And that's a lot of work to go on the end and find a mistake. So being able to double check is a lot better than just letting it go. All right. So when you're condensing resistors, you'll have your single resistance, a current and voltage. You can simplify the resistor down to one resistor and one battery. So this, again, not really important for what we're doing today, but this idea will be really useful when we start talking about combined circuits. So you can see we have 4 resistors here. And because they're all in series, we have one wire connecting each one of them, one full loop. We can just add those resistances together. So we get our equivalent resistance. That's the step 1 that's up here. So we're pretty much just dealing with one battery and one resistor. That's what they mean by equivalent resistance, or total resistance if you want. Because you're just taking the circuit and you're trying to simplify it so it doesn't look so nasty. Again, this isn't very nasty, but it will get nasty. I promise. It's like a big puzzle.
Yeah, and that means current's 24, right?
Yep. Equals IR. 6. No, I can't do right. Be 6 over 18.
Okay.
So this is a grid. Wow, it does not look very good up there. Okay, I'm going to rewrite it on the board to help you. And this grid I use for every single one of my circuits. You can see at the top here we have, well, let's start with the side. We have VERP. And across the top here we have the numbers of resistors in your circuit. So if you have 10 resistors, you're going to have 10 columns. If you have 3 resistors, you're going to have 3. So let's say that we have 3. So you have one for each resistor and the total. So in the R column, you would write down the resistances for each one of your resistors. And your resistors, a lot of time, the way the book talks about it, it'll say like resistor with the one that's the resistance 6, and one of them is 10, and one of them is 8. Yeah, I just kind of skip all that, and I just label them 1 through 10, or whatever, how many resistors there are, so they each have a resistance number. So it doesn't really matter what those resistances are or what order you put them in. Just give them some sort of label, 1 through however many resistors you have. And then you'll write that down. So remember, resistance is in ohms. So let's say we have 3 resistors in series and they have 1, 2, and 3 resistances on them. So we're going to add up our resistors. We have 6, so our total is 6. Let's say the battery is, I don't know, 6 volts, and that'll be something that's given. So this is given, this is given, this is given, and this is given, usually in your circuits. So I added them up using the first step. Solve my total resistance is 6. Now voltage is usually given, so we're going to solve for I. So use V equals IR. So 6 equals I6, so this is going to be 1. Since in series, our current is constant, current's going to be 1 for every single one of those. And then we'll use V equals IR to solve for V. So I times R is V. This is usually as far as your book is going to ask you to go, but I'm asking you to go just one step further. Once you filled this out, that's the easy part. I want you to use P equals IV to double check your circuit and make sure it's right. So we're going to go V times I. And down here as well, V times I. And then here's the double check. So we use P equals IV. We're going to add up all our P's and make sure they equal that total that we just got. So we're going to go this plus this plus this equals this. And does that work? Yes. So we know we did it right. With most of your circuits, it's going to be a little bit off depending on how many significant figures you keep. So you might get 52 on one of them and 52.2 on another. If they're really big numbers and there's a very complicated circuit, you might get something like 512 and 514. It's probably okay. Just look at your significant figures, but don't worry about it too much. You're just looking for it to be kind of close. Okay, so how to solve? Example of it solved. And I know that this one's really easy, but again, it's going to get more complicated. So let's do a practice problem. A potential difference of 300 volts is applied across the system of resistors. So they just told us that our battery is 300 volts. We have resistor 1 is 40 ohms, resistor 2 is 100 ohms, and resistor 3 is 60 ohms. So I want you to write down this grid, fill it out, and solve. I want you to tell me what is the resistance of the system, the current, the potential difference, the power for each resistor, and the final power of the whole system, using this exact same thing that I just did. And if you look, A through E walks you pretty much through every single step. let's start solving this thing here. Okay, so I see that my battery is 300 volts, so 300 is going to go up here. And I have resistor 40, 100, and 60. Now, most of your resistors in your book are not going to be labeled 1, 2, 3. It doesn't matter what order you do it in. It'll be fine. Especially for series, not a big deal. So, because it's in series, we're going to add them up. So what's our total resistance? 200. What's the next step? Calculate I. So we use V equals IR of just the total. So total V equals total I equals total R. So we're going to have 300 equals I times 200. So 300 over 200 is 1.5. What's the next step?
Calculating resistance by multiplying things.
Current is constant.
Current's constant. That is a big step. You're going to see that that's one of the most important steps when you're doing combination circuits is what is constant. That's what you're going to go back to. If it's in series, this is constant. If it's in parallel, this is constant. So since it's series, our I is 1.5 for every single one. Now what?
Solve for individual potential differences.
Good. We're going to solve for V equals IR for V on each single one. So 40 times 1.5. 1.5 times 100. 1.5 times 60.
90.
Good. Now what?
Solve for powers.
Solve for power. P equals IV. Solve for P. 60 times 1.5.
90.
150 times 1.5.
225.
90 times 1.5.
135.
And 300 times 1.5.
450.
Now I want you to double check. I guess we should add that down here. Double check. P1 plus P2 plus P3 should equal P total. 90 plus 225 plus 135 does it equal 450. Yeah, it does. So we're good. We've completely solved that entire circuit. How do you guys feel about this?
Good.
Not too bad. It's going to get worse. Not yet. All right, we have some clicker questions for you today. I don't think that they're very hard. I'm pretty sure they're like super duper easy. Here's our first clicker question. It says 2 ends of a 3 ohm resistor are connected to a 9 volt battery. What is the current in the resistor? You have to bear with me. My clicker program is leggy today.